Hi guys, welcome back to my mathematics tutorial. Again, my name is Peter C. Doper Jr., your math tutor and instructor of mathematics at the University of Liberia. So in this lesson, we want to continue with example 73 and 74 under solving differential equations. And like we started in the previous lesson with reducible to variable separable form of this type of differential equation. So whenever we have this type of differential equation, we say we can bring in a substitution that reduces that differential equation into variable separable method. So we have another example. So we want to look at two additional examples. So this example says x minus y all square dy by dx equals to a square. Similar to the previous one we did that says x plus y all square dy by dx equals to a square. So now, always do not just see a differential equation or a calculus problem as a whole and just say it's easy and you can solve it. You don't learn math by looking, you learn math by practicing. Sometimes you see a problem, it looks very easy, but the moment you start to attack the problem, it turns out into something that is very, very challenging. So always put your pen to your paper. So now x minus y raised to the second power dy by dx. So again, we allow x minus y to be some variable, because if we expand this thing, you're going to have something in this form. We expand this thing, right? So if we have x squared minus 2xy, the expansion for this now, plus y squared times dy by dx, it will be very difficult for us to just separate these variables, the x and the y variables, and integrate. So we can substitute first before separating the variables. So now we have let u equals, so you don't have to use a particular variable z or something, you can use any other variable. So we say let u equals to x minus y. So u is a new variable that we've brought into the problem, it's a new function. So now we have two functions, u and y. Now we differentiate both sides of the function of this equation. We have du with respect to the independent variable x dx equals, now the derivative of u is just 1, but since we are differentiating a function, we attach du by dx. The derivative of x is 1 minus the derivative of y is also 1, so we also attach dy by dx since this y is a function as well. The next thing is to solve for dy by dx. That's our next target. So we can send this, okay, because it's negative, so we can send this across. We have dy by dx is equals, we send this one across, 1 minus du by dx. So we've gotten the value now for dy by dx. We're just going to replace it within this expression. So we have x minus y. X minus y is just u. So it's u squared, right? And then dy by dx. What is dy by dx? So dy by dx now is just 1 minus du by dx equals a square. So our next move now is to separate the variables, because we can easily separate the variables down from this. So we multiply u squared times this is u squared times this is u squared du by dx, all equals to a square. So we can separate the variables. If we multiply this entire expression by negative, so we will have negative u squared positive u squared du by dx, all equals to negative a square. So we send this u squared across, we have u squared du by dx is equal to u squared minus a square. So what's next? We can divide both sides, because we we need this dx to be on one side and du be one side so that we can integrate both sides, right? So we can just cross multiply. So it's u squared du, and then this time this is u squared minus a squared now dx. So this is x. The integrating variable here is x. So we need only x within this parenthesis. So we must get rid of this entire expression. So it's u squared minus a squared, u squared minus a squared. So this carry this out. We're left with now u squared du, u squared minus a squared, all equals to dx. Now the variables have been separated. On this side we have the integrating variable is u, and on this side the integrating variable is x. So we can now integrate both sides to find our general solution of this differential equation. So what do? Like in previous video, you can apply long division. But since I already showed you the technique, you just rewrite this u squared as u squared minus a squared plus a squared, because minus a squared plus a squared goes to 0. So we say divided by u squared minus a squared du. And the integral of the x is just equals to x. So we can separate this, the first two terms. So we take u squared minus a squared divided by u squared minus a squared du plus the integral of a squared all over u squared minus a squared du equals to x. So this is just equals to 1. So this is now the integral of 1 du plus a squared, the integral of du all over u squared minus a squared, all equals to x. So the integral of 1 du is just u, and the integral of du all over u squared minus a squared is just 1 all over 2a. That is what is here, right? So if this was 3 squared, it will be 1 over 2 times 3. So 1 over 2a, the ln of u minus a all over u plus a equals to x, plus some arbitrary constant c. So what do we do next? We further simplify. What is our u from the onset? U was x minus y. So this is x minus y plus a squared. Now this a can cancel 1 from here. So we'll just be left with a over 2. The ln of u now is x minus y minus a, x plus x minus y plus a, and then equals to x plus c. So this x cancels this x, right? And then we're going to have minus y plus a all over 2 ln of x minus y minus a all over x minus y plus a equals to c. So if we let, we can solve for y. So therefore we can say we multiply this whole thing by minus 1. It means nothing. So you have y. So this now will be negative. If this goes across, it becomes positive. So it's going to be, this is going to be y equals to a over 2 ln of x minus y minus a all over x minus y plus a. So this negative also times this c is negative c, but it's just a constant. That c is just an arbitrary constant. So it doesn't have to be negative c or 3c or 5c. Whether you have 10c or negative c or whatever the case might be, at the end of the day, just replace it with some arbitrary constant. So this c, we just replace it with positive c instead of saying negative c or something else, because it's just a constant. It's an arbitrary constant. So this is our final answer. So you can decide to rewrite this, whatever way you want to rewrite it, like by saying this is the power, like r, the ln of a is equals to the ln of a raised to the power r. If you want to make this to be the power of this expression, it's no problem. You can do that. Okay, so we solve another problem quickly. Okay. So we have 4x plus y. So dy by dx is equals to 4x plus y plus 1 raised to the second power. Now, why do we also have this problem? So this function is also of this form. So we can say let some variable u equals to 4x plus y plus 1. What do we do next? We find the derivative. So we differentiate both sides. We have the u is equals to 4 plus this is dy by dx. This is 0. The derivative of a constant goes to 0. Next thing we need to do is to solve for dy by dx so that we replace this dy by dx. So we have the u by dx minus 4, that is we send this 4 across, equals dy by dx. So we replace this dy by dx now within this original equation. So we're going to have du now dx minus 4, that is the substitution for dy by dx, equals, now what is here is just u, so it's u raised to the second power. We can now separate the variables and solve. So we have du by dx is equals to u squared plus 4. So what do we do? Cross multiply. So du now is equals to u squared plus 4 dx. Again, this is x. So we only need x right there. So since the variable in here is not x, we have to get rid of it. So we divide both sides by u squared plus 4. We divide this out by u squared plus 4 as well. So this cancel. You have the u over u squared plus 4 is equals to dx. So we now integrate both sides. So we can rewrite this as du all over u squared plus 2 raised to the second power. And we know that the integral of dx all over x squared plus a squared is just equal to 1 over a tangent inverse of x over a plus some arbitrary constant c. So similar to this problem, this u represents the x, a represents 2. So this will now give us, now the integral of dx is just 1, it's just x. So this now gives us 1 over a now, which is 2, tangent inverse of u over 2, or equals to x plus some arbitrary constant c. Now what do? We replace our u. Our u is what? 4x plus y plus 1. But let's further simplify it, right? Now let's get rid of this 2. We can multiply all sides by 2. It means that this will be tangent inverse of u over 2 is equals to 2x plus 2c. And again, it's just going to be represented by some c, right? Because it's still a constant. Now, we also know that tangent inverse of x is just equals to x. Composition of functions. So if we take tangent on both sides, u over 2, we take tangent on both sides, 2x plus this 2c. Now we just replace it with some c, right? So if we take tangent on both sides, tangent of tangent inverse of u over x would just be equal to the angle, which is u over 2, not x, u over 2, right? Equals tangent 2x plus some arbitrary constant c. So if we cross multiply, we have u now to be equals to 2 tangent of 2x plus c. So what is u? Let's bring in u now. U is 4x plus y plus 1. So u is 4x plus y plus 1, or equals to 2 tangent of 2x plus some arbitrary constant c. So there's our general answer. If we left, we can solve for y by saying 2 tangent 2x plus c minus, we send this 4x across, minus 4x